Hi everybody. I'm very happy to introduce Andrew Hill. He's been working with me for just over a year. He came back from India full of enthusiasm for a project, and I worked my best to grind that enthusiasm out of him by throwing difficult projects at him. So I don't think I was successful. Andrew still meets with me on the regular to discuss research progress and has shown a great deal of dedication to what ended up being a very challenging project. So I was really excited when Andrew first came to me. We talked about the research ideas, and he found a paper that had something very intriguing in it, so we decided to chase after it, which, great idea though it was also a great challenge. So he'll tell you a little bit about that today, and then he'll tell you about some of the, I think, more promising directions that we've been heading in as of late. I should say Andrew comes from Madison, Wisconsin, and I think we'll be heading to Tennessee for the near future. It sounds like you're in talks with someone at Oak Ridge National Labs, perhaps, so strengthening our relationship between Lawrence and Oak Ridge, which is never a bad thing. So I'll let Andrew take it from here, so help me welcome Andrew to the stage.
Well, yeah, thank you all for coming today. I'm going to be talking to you about research I've been doing in Dr. Sazma's lab for like a year and a half now, as he said. So we're, as the title suggests, looking at the redox properties of different ligands, and this represents a first step towards creating a material with electrically conductive properties. So this, again, it's a baby step, but it would be with the purpose of creating a new material, which would be most likely a semiconductor here. So we have pictures of some great silicon crystals here, and most of the electronic components that you are used to interacting with in your daily lives, in your computers, cell phones, what have you, and here in very large solar panels are made out of silicon. And there's a lot of momentum behind the development of new technologies with silicon, and we are very good at doing so. However, it does have a couple of inherent properties that perhaps make it not the best choice for every application. So as it says up there, it is a brittle crystal. And crystals are, they take time to grow, therefore making them expensive. I've grown a couple of crystals over the course of this project. And then also, when you're working with a crystal, it is like Michelangelo with his slab of marble trying to create the statue of David. So here on the left, we have a picture of a transistor. So these are one of the essential components of electronic devices. And as it says on there, it's a 14 nanometer transistor. This is about the limit of what we can currently do via this etching process. So for some perspective on 14 nanometers, a sheet of paper is like 100,000 nanometers thick, and a nanometer is like how far your fingernail grows in 10 seconds or something like that. So if you wait a little bit, you'll see it has not gone very far. So again, this is a very, very small thing, and it is a huge achievement that we were able to make these things by etching them. But again, if we want to continue to shrink this down, eventually we will hit the limits of what can be done via this etching process. So one alternative proposed for that are so-called molecular materials. So flexible in that you could make this thing thin enough to be truly flexible, but also in that when you're doing these things, they often start from liquid precursors, so you can literally put these things into an inkjet cartridge and print them out. And you're starting from cheaper materials, so this can lead to rapid and efficient prototyping of new devices if you could get these materials working. So the best molecular materials that are electrically conductive that we have right now are conducting organic polymers. And I would like to help us understand how conductivity works at a molecular level. So it comes from, usually in organic systems, the overlap of p orbitals. So we have two hypothetical atoms here on the board, there and there, and their p orbitals are aligned just so to make what we would call a pi bond. So this is a computer model that I made. Again, our atoms are here, and now because those orbitals were aligned properly, they can mix and give what's called a pi bond. And so now these two large lobes, instead of the four lobes you saw before, represent where the electrons are likely to be found around these two nuclei. And this is true also for extended systems. So if we look at a longer chain of atoms here with their p orbitals properly aligned, we get a long orbital. So I am a sailor, and if I were on my hypothetical electron boat here, I would now be free to sail across all of that territory. If the weather's good, on the other side of the carbon chain, an electron could go over there for the day. So this is also true in two-dimensional systems. This is a picture of graphene, a well-known material. It's in your pencils and all that, and it is a well-known organic conductor. So like that little picture on the right shows, the p orbitals here, because it's a flat structure, are all able to align properly. And then a computer model of this one shows that the electrons are spread over the entire thing. So again, our boat now has kind of a lake to go through instead of like, maybe the last one was the Fox River for the straight chain. So I'm interested in making materials that involve both organic pieces and metal atoms. So to do that, we also need to take a look at the concept of oxidation and reduction. So typically, we think about these things, which are core concepts from general chemistry. It's the loss and gain of electrons. So here we have a nickel atom with its 10 electrons. And we think about oxidation and reduction happening on metals fairly easily. So if we were to focus on just one of these electrons, and then some kind of oxidizing agent were to swoop in and run off with one of our electrons, we now have nickel plus, or nickel 1. So it's become an ion. It is deficient in electrons. And that works the same way in something that's involving a slightly more complicated molecule. So here again we have the nickel atom, and then it's held onto by two pieces of organic material called ligands. And again, we have our electron, and our oxidizing agent comes in, runs off with our electron, and we think about it as becoming nickel 1. So we've changed the charge, but that charge is localized on nickel. It had very little to do with the ligands. However, relatively recently in the field of inorganic chemistry, it's been discovered that some ligands can do this as well. So here we are with our electron thief. We have an overall 2- compound of nickel 2 and 2 stilbene dithiolate ligands. So in the typical case, for the oxidation of a complex like this, we would expect him to grab a nickel electron and we would get to nickel 3 or something. Now, if you know much about transition metal redox states, that would seem suspicious to you. But in fact, it has been shown spectroscopically that it comes from one of the stilbene dithiolates. So our nickel 2 is still nickel 2, and we've taken an electron from here in the ligand. And again, we moved from an overall 2- compound to a singly anionic species. And then we can take another ligand electron away to get to the neutral species. So this is, as Stefan Demmert would say, non-trivial to find a ligand like this. It requires a very special type of ligand that is redox active, we would say. So it's able to lose and gain electrons, kind of like a metal. We think of being flexible in that way. And then this is very important for the concept of redox non-unisons. So this is where you take away an electron from a complex like this one. It's cobalt held onto by two NAC ligands. And you say, did this come from the metal? Did this come from the ligand? Well, it kind of came from both. So this, again, we're looking at a computer-generated model of where to look for the electrons. And a bigger lobe means it's more likely to be there. So this electron spending most of its time hanging out on the cobalt, but you also find that it is dispersed spatially out onto the ligands. So this is promising from our standpoint, trying to design molecular electronic materials, because if you could hook these up in some kind of a way, attach another NAC and another cobalt over here, you could have an orbital that extends across the entire thing, and like we were looking at with the electron sailboat before, then you can move a charge through the molecule, and that is the essence of conductivity. So here's an example from the literature of a successful conductive metal organic material. So this material shown on the board with the nickel atoms in place is actually a record setter for the highest electrical conductivity reported in a material of this kind. However, one of the great things about these is that you can interchange the ligands and the metals. So if you were to build a structure using the same ligand, but with copper instead of nickel, it lowers the conductivity down into the semiconductor range. So this is a measure of conductivity, 0.2 Siemens per centimeter. That's in the semiconductor range. With nickel, I believe it's 2 Siemens per centimeter. And some perspective on that, a copper wire goes at about 10 to the 5th Siemens per centimeter. So this is far, far less conductive than that. Whereas, something you think of as an insulator would be, 10 to the minus 10th or whatever. But interestingly, these structures are both more conductive than silicon and germanium, which are commonly used for electronic components at the moment. So another great thing about being able to change the structure is that you get some added functionality with the copper atoms that you didn't have with the nickel atoms. So this material, when it's built with copper, is sensitive to ammonia vapor. So it's not all about just trying to make the most conductive material possible. There are applications for various levels of conductivity, as well as for various other functionalities that you could get to. So we actually have a word for these kinds of metal organic materials, and it is a MOF. So what is a MOF? It's a metal organic framework. So it is one of these extended structures that we've been looking at in 1, 2, or 3 dimensions that are connected by ligands. So I like to think of this as the molecular tinker toy set. So in this analogy, these wheels are the metal atoms, and then the sticks that hold them together are struts. They are the ligands. And one of the important features of the ligands that go into MOFs is they are multitopic, which means that they can bind to multiple metal sites. So these sticks that you get in your tinker toy set would be pretty useless if they didn't have an end that could go into another thing and make an extended structure. And similarly, we need special kinds of ligands. So over here is an example of what we would call a monotopic ligand, ammonia. And it sticks onto a metal as shown through its nitrogen atom. So it has electrons to donate to making that bond. But then the H3 half of it is not useful for making bonds to metals like this. So you can't make any kind of extended structure. However, a ligand like pyrazine, which has these nitrogen atoms on both sides, is actually able to bridge between 2 metals. And you can imagine if we were to make a chain out of pyrazines and tinker toy pieces, looking something like this, you could hook up a indefinite amount of them, and then we would have a polymer. So that's an example of a ditopic ligand. There are also tritopic ligands, like this one, HITP, which is what we just looked at on the previous slide. So it makes the two-dimensional sheet because it is able to hook up to 3 metals. So way back in the dark ages of my project, last winter term, these were the first class of ligands that we came up with to try to make. So like that picture we were looking at for the redox non-innocence, this is basically exactly that idea of lifting that molecule out of the paper with these knack-knack pieces and then putting in some kind of bridging species that would have available pi bonds to pass ligands through, and then we could create a one-dimensional chain of cobalt and these ligands. So the way that this is made, at least the carbon structure of it, you can see this had oxygens instead of nitrogens. The plan was later to replace those. But we are doing a transition metal catalyzed cross-coupling reaction. I'm not going to dive too deeply into the mechanism in this talk, but we can take our diiodobenzene, and basically the copper is able to wiggle into this bond and then also make a bond to acetylacetone and wiggle out of it, leaving us with the groups installed in the proper places in the molecule. One of the great challenges to reactions like this is that they have to be performed free of oxygen and water. So water is a particularly big problem because if it gets into this reaction, we're actually going to lose one of the functional groups that we needed to have our ligand functioning properly. And at the time, we didn't have a great way around this. Actually, over the winter, we now have a functioning glove box. So this is a space, the inside of which is free of oxygen and water, and you stick your arms in the gloves and can work with stuff inside there. So that may have potentially improved the results of those reactions. And it also came to my attention while working on this thing that geometrically it might not have panned out anyway. So one of the characteristics we were looking at early on with the computer models of the pi bonding is that you needed a flat surface. And here, there's actually some interactions between the hydrogen that you don't see here and the hydrogens you don't see here that cause this molecule to twist. So this is a known crystal structure. And you can see that instead of being flat to each other, they're actually twisted 77 degrees. And if it's less flat, it's less likely to be conductive. So after several months of labor in that direction, we came up with a new plan, which is to make this type of ligand. So this Y here is not yttrium. It is shorthand for oxygen or sulfur. Again, in one of these flat ring systems to allow electrons to pass back and forth through it. And then these nitrogen atoms, which as you've, I'm sure, noticed over the course of this talk, seem to be the chosen way to attach to metals. So retrosynthetic analysis is a fancy word for looking at the after picture and saying, what before do I need to make this thing? It's pretty straightforward because this molecule called dibenzofuran is a common side product of crude oil refinement making petrochemicals. And then we just need to somehow put on these 4 NH2 groups, which sounds very straightforward. Is slightly less straightforward in actuality because this ring system and NH2, or just ammonia, have no desire to actually react with one another. So the way that you do this is by adding nitro groups and then reducing them. So this is a reaction that involves fuming nitric acid to let you know if you're unfamiliar with this. There's concentrated acids and then a level beyond that, which would be the fuming acids. So this happens to be a liquid at room temperature, a yellow liquid, HNO3. So this is a waterless version of the acid. And then the solvent is also neat sulfuric acid, so that is, it allows you to transcend the level of acidity that you can find in water-based systems. So how this works is the double bonds of the ring kind of reach out with their electron arm and grab the very electron-hungry nitro group, and you lose an equivalent of water. And the new bond is shown there in magenta. However, the thing about this, it just said it's a very electron-hungry group. Once it is attached, the electron arms, I guess, get shorter and shorter and have less ability to grab onto more nitro groups. So I was never really successful in attaching more than 2 of these to the ring system. So one of the possibilities we considered was that the acid was not weak, that it was contaminated, was too weak, excuse me, not strong enough, contaminated with water perhaps. So we didn't have the concentrations that we wanted to make this reaction go. So this is a little test that we saw on the internet to see if your fuming nitric acid was fuming hard enough. This is a nitrile glove, which is not supposed to be easily oxidized or combusted. So don't try this at home. I don't know how you would, since you probably don't have this acid around. But there was a fire extinguisher at the ready and all. So we decided to put some of this onto a nitrile glove and see what happens.
Woo! Hell yeah! Oh, I hope it goes out soon.
All right. So that seems to not have been the problem based on that. So we moved on to a different strategy to attach those amine groups, which is what you might call the more modern way to do this. So first, it's a bromination reaction, which proceeds by the same mechanism, where the ring is reaching out with the electron arm and grabbing onto bromine atoms. However, these have the advantage of being less electron hungry once they're attached and allowing the reaction to proceed. And from there, we can do another transition metal catalyzed cross-coupling reaction, this time with palladium. And basically what this is doing is, again, wiggling into this bond, also grabbing onto the nitrogen, and then leaving us with the bonds that we wanted. So this is called benzophenone imine. I will be referring to it as the red group for the duration of this slide. And then it's a fairly straightforward treatment with acid to remove the red part of this and leave us just with the nitrogen that we were looking for. And this is where I currently am. I have some of this sitting around. It's been through a column, so hopefully it is pure and just waiting to be treated with acid. So we're fingers crossed, only days away from seeing the final product, for which we have good-looking DFT results. So this is, again, another computer model of spin density. So this is of the oxidized species. It has unpaired electrons. So this is showing us where the unpaired electron is likely to be found. And this is the complex with nickel. So these are the 2 nickel atoms, and you can see that it is localized there, but then it is spread throughout the entire ligand as well. So we're thinking the chances are pretty good that in a long chain of these, we would be able to pass electrons through it. And then I would just like to thank the people who've helped me along the way. So the Lawrence University Faculty Research Fund for funding all of my lab work, Dr. Sazman for his guidance, Dr. Dever for many consultations on the organic reactions, Elizabeth Bridgewater, who is here today. She did quite a bit of the early experiments along with me over the summer. Daniel Martin and his assistants, who humor me on a daily basis. Michael for being instrumental in getting the glove box up and running, and then Deanna Donahue and Dave Hall for their feedback on the presentation. Thanks a lot.
Are there any questions for Andrew?
Yes.
Allison, please. Andrew, you can call him people.
For applications in semiconductors, especially for the solar cells, you have to have some sort of input, so photon-induced excited electronic state. And so I'm curious, what sort of recombination pathways are there for these larger MOF-like systems? Because it seems like there would be more opportunities for recombination to occur before the electron could make its way conducting wires to the external circuitry.
So the recombination of charge
right, so
as it's moving through the...
Yeah, so your excited electron goes up into the excited state, and then it'll do everything it can to find its way back down again. So I'm curious if having such a large structure of these polymers, you introduce alternative ways that these electrons will recombine before, or relax before they can get into the actual, using it for power.
Yeah, I think I might have to gracefully bow out of this one. My understanding of actual solid state physics is pretty non-existent. I can say that some of the neutral states of these, like this molecule, its neutral state also is very close in energy between the singlet and quintet state. So the quintet electrons should be able to move because they're unpaired throughout this without feeling the need to recombine full charge wise. But yeah, and some of the other things that we're looking at, the results with cobalt as well show good charge neutral conductivity.
Cool.
Yeah.
It's when Graham was introducing you, as well as several times throughout your talk, said, this is as far as I've gotten, and then Graham mentioned some challenges. So could you give some context to what sort of things were really challenging in the synthesis process for those of us who have no idea what synthesis actually is?
Yeah. So there's quite a bit of digging through literature for things that look similar to what you want to do, and then you just kind of cross your fingers and hope that it will work on the system that you're using, which is not always the case. I try to convey some of the challenges with water in that, but then also that reaction was producing some of the correct material. Here, I actually have quite a few more slides. Oh, this one was amusing in that this is the thiophene version of what we were trying to do, so the conditions are exactly the same. However, this was so unstable to heat. You can see we had to heat this one to 100 degrees Celsius, and it would just blast off the iodines as you heated it because they had no desire to be there any longer. So that was about a term, spring term of last year, trying to figure out why that wasn't going. Pretty simple and not very satisfying explanation. This is an example then of that reaction I was showing with water contamination, right? So we would end up with all of these things. This is the product that we wanted. This one only attached on one side. This one has lost a group on one side. This is from both sides. So we would end up with all of these things in the pot, and then you want to separate just this one from it. So the most common technique for doing these things is column chromatography, where you're essentially separating things based on how different they are from one another. And these are incredibly similar, it turns out, in terms of their properties and their interactions with silica gel. So it was very difficult to separate those things.
Okay, if there's no more questions, let's thank Andrew again.